Hello students. So in the last lecture we saw a very beautiful concept of continuity equation in quantum physics, which tells us that total probability is conserved. We started with the probability density and that led to the existence of current. This is embedded in the Schrodinger equation and we all are solving that Schrodinger equation. So it has to be there. Now let us try to get a deeper insight of this probability current by doing some examples. Okay, so we'll start with some potentials and we'll try to see how it goes. Okay, so let us try to take the case of quantum mechanical scattering in step potential. Scattering in step potential. So how does it look like? It looks like a step. So this is my potential barrier V naught, and here this is at x is equal to 0. When x is less than 0, the potential is 0. When x is greater than 0, the potential is constant V naught. Okay, and so there may be two cases that the particle which is coming, it has energy here. This is the case of energy E greater than V naught. This is my case 1. Okay, the particle can also have energy less than the potential height, barrier height. Okay, we'll see that case later on. Now in this case, what will happen? What do we expect classically? Classically, the particle will cross the barrier. Obviously, when the energy is greater than V naught, so we have some positive kinetic energy and it will cross the barrier and will always be transmitted okay. Now what do we expect quantum mechanically? Quantum mechanically, I am claiming that mechanically the particle has finite probability of being both reflected and transmitted. Has finite probability of being both reflected and transmitted. Now we'll try to see that how we can show this. Transmitted where? In region 2. If I call this region 1 and I call this as region 2, then the particle is being transmitted, has finite probability of being reflected and transmitted. Okay, so now let us try to see the wave functions in both the region 1 and 2. Excuse me. Sorry. So now, yeah. Okay, so now we'll try to see whether it happens or not, or what do we understand by this. So how do we proceed? We'll try to write the Schrodinger equation in region 1 and 2. Okay, so let us start. In region 1, my potential is 0. So my Schrodinger equation will become d2 psi 1 by dx square plus 2m upon h cross square E psi 1 is equal to 0. Okay, the potential is 0. In region 2, here the potential is V naught. So my Schrodinger equation will become d psi 2 by dx square plus 2m upon h cross square E minus V naught psi 2 is equal to 0. And energy E is greater than V naught. So now, calling this 2m upon h cross square into E is equal to k1 square and 2m upon h cross square E minus V naught is equal to k2 square. We get the two equations as d2 psi 1 upon dx square plus k1 square psi 1 is equal to 0. Psi is a function of x. Okay, d2 psi 2 upon dx square plus k2 square psi 2 is equal to 0. Okay, and we know that the solution of these, so what is this? This is a second order linear homogeneous differential equation. And the solution, we have already seen the solution of such an equation is oscillatory. So what do I get? Psi 1 x is equal to a e to power I k1 x plus b. So this is at x less than 0, and this is my equation is x is greater than 0 in region 1 and 2. b e to power minus I k1 x. Okay, at x is less than 0. What is k1? 2me upon h cross square. And psi 2x will be c e to power I k2x. I will not have any coefficient with e to power minus I k1x because in my problem here there is no boundary, nothing to get reflected. Okay, so my solutions are these. Now what we have to do, we have to find these coefficients, and that we already know that we can find these coefficients by using the boundary conditions. To find these coefficients, using the boundary conditions. Okay, what are the boundary conditions? That my wave function, the wave function and its derivatives are continuous across the boundary, and here at x is equal to 0. Okay, so when I put at x is equal to 0, psi 1 x is equal to psi 2 x, and d psi 1 by dx is equal to d psi 2 by dx. This is at x is equal to 0. This is also at x is equal to 0. Okay, by substituting this, you will see from these two equations, equation number 5 and equation number 6. This is x is greater than 0. From equation 5 and 6, when I put at x is equal to 0, 7 is equal to psi 2, I will get a plus b is equal to c. Okay, a plus b is equal to c. And when I take the derivatives, I will get I k1a minus I k1b is equal to I k2c. These are the two equations which I will get. So we can name them as equation number 7 and 8. Okay. So I can also write these equations as a plus b is equal to c, and the second equation I can take I k1 common, a minus b is equal to k2 upon k1c. Okay. From the equation 9 and 10, we will see the quantity of interest would be the ratios. We have two equations and three constants. So we can find b upon a from this equation as k1 minus k2 upon k1 plus k2. This is my first result. We'll see how this result is important to us. Okay. C upon a is equal to 2k1 upon k1 plus k2. Okay. We name this as equation 11 and 12. Now, we can show that here the total probability is conserved. That we already know from the last lecture. Those who don't have idea, please go through my previous lecture to get the derivation for that. Now, we can imagine that in this step potential, the probability current, whatever current is flowing, here if I take region in region 1 and in region 2, the probability current, whatever current is coming from region 1 should be same as in region 2, because the probability is conserved. It cannot go anywhere. The current coming from region 1 should go to region 2. So we can write that, and from the last lecture we have derived that probability current density, current at point x, density at some point x, that is j of x, is given by h cross upon 2im psi star del psi by del x minus psi del psi star by del x. This I have derived in the last lecture. So kindly refer to my previous lecture to see the derivation of this. This we have already derived. And here you can see that if this is a complex number z, then this is z star, the complex conjugate of that. Yes, and z minus z star gives 2 times imaginary part of z minus z star. So I can also write gx as h cross upon m imaginary part of psi star del psi by del x in a much cleaner way. Yes. Okay. Because how do I get this? Z minus z star is equal to 2i imaginary z. Okay, this is z minus z star. So I have written 2I times imaginary of z, and I will get this because. Now let us try to see what current do we have in region 1. Okay, when x is less than 0, the current in region 1 is, by substituting in this formula, h cross upon m imaginary psi star del d psi by dx. Psi we know in region 1. Already we have written the equation here. This is my psi in region 1. So you have to take psi 1 star and the derivative of d psi 1 by dx. And you have to find j1. This is a small exercise which I would like you all to try. You will get h k1 upon m a square minus b square. Okay, and in region 2, h cross k2 upon m c square. Okay, you can write this as mod. Get the mod coefficients. So we need to show that J1, whatever current is coming from region 1, is same as region 2. Then only there will be a current conservation. Okay, the current on the left is same as that on the right. And also a very important point to note here is that it does not depend on the value of x. It is a constant. That's very, very important. So current conservation is encoded in the Schrodinger equation, and we have to get this. So now already we got some relations between A, B and C. I want to show this. How do we get this? From equation number 11 and 12. I call this as equation number 13 and 14. Now from equation in J1, J1x is equal to h cross k1 upon m. I take mod a square common, then I will get minus b upon a whole square mod a square. Substituting the value of b by a from equation number 11, this is this equation k1 minus k2 upon k1 plus k2. If I substitute, what do I get? H cross k1 upon m 1 minus k1 minus k2 upon k1 plus k2 whole square mod a square. When I solve this 1 minus, I will take k1 plus k2 whole square as LCM, and then by solving this I will get h cross k1 upon m, and inside I will get 4 k1 k2 upon k1 plus k2 whole square into mod a square. Now if I take k2 outside here and k1 here, I will get h cross k2 upon m 4 k1 square. Okay, so I can write this my j1x is equal to h cross k2 upon m 4 k1 square upon k1 plus k2 whole square. This I can write as h cross k2, sorry, this is k2 upon m 2 k1 upon k1 plus k2 whole square mod a square. And now I can see from the equation 12, c by a, it is 2 k1 upon k1 plus k2. So 2 k1 upon k1 plus k2 is c by a. So if I substitute this k2 upon m mod square correct? And what do I get? H cross K2 upon M mod C square. Now what is this? This is my current in region 2, and we can show that the current is conserved. Now this is very nice. It has to be there. This is equal to J, which proves that current is conserved. This is by current conservation. Okay, this was a small exercise which I wanted you all to just check. Okay, now my current in the left region I can write as J. In region 1 I can write as JA, the current incident minus current reflected. Okay, where JA, just I'm H cross K1 upon M A square is JA, H cross K1 upon M B square is JB. Okay, just I'm defining, where JA is H cross upon M mod of A square K1 minus H cross K1 upon M mod of B square. This is my J1x, and my J2x I can write as H cross K2 upon M mod of C square. This is equal to JC. So this is my incident current, and this is my reflected current, and this is my transmitted current. Now this suggests that we can define the reflection and transmission coefficients. And the definitions are correct, that R, the reflection coefficient, is JB upon JA, the reflected current upon the incident current, that is equal to H cross K 1 upon M will cancel, K1 minus K2 upon K1 plus K2 whole square. This is my reflection current. Now we can also define the transmission coefficient T. This is reflection and the transmission coefficient. Obviously this is JC upon JA, the current transmitted in region 2 upon incident. This will be K2 upon K1, because JC is H cross K2 upon M and JA is H cross K1 upon M. C upon A mod square, which is equal to C upon A mod square. This is equal to, so it will be K2 upon K1, 2 K1 upon K1 plus K2 whole square. This is equal to 4 K1 K2 upon K1 plus K2 whole square. This is 1, sorry. What does this show? That quantum mechanically, which I have claimed in the first statement, quantum mechanically there is a finite probability of the wave being partly reflected and partly transmitted. So my R coefficient is finite and my T is also finite, which shows that the particle is partly reflected and partly transmitted even when the energy of the particle is more than the potential barrier. Also we can show a very nice thing here, that if I take my R plus T, this is equal to what it should be, total reflection whatever incoming wave is there, some part is reflected and some part is transmitted. Nothing can go anywhere. So it has to be 1 r plus t, and which we can show that jb upon ja plus jc upon ja, this is equal to jb plus jc upon ja, and we know that we have proved here on the left hand side. I'll do, because j in the one region is equal to j in the second region. This already I have proved. And what is ji? I have written ja minus jb, this is equal to jc. This already I have proved. So jb plus c is equal to ja, and it comes out to be 1. And we can check from our coefficients. I can just name these equations as, I forgot to label the equations, 12, then 13, 14, then I can write this equation number 15, equation number 16. Okay, sorry, this is 17 and this is equation 18. That from equation number 17 and 18, if I check r plus t, this is equal to k1 minus k2 upon k1 plus k2. This should be plus 4 k1 k2 upon k1 plus k2 whole square. If I add this to equation, this comes out to be 1. This is indeed a very beautiful to see that total current is conserved, and I got a lot more insight of this, that total probability is conserved. Whatever current is coming from the left region is going in the second region, and this we can easily see in terms of the reflection and the transmission coefficients. That my reflection coefficient, that there is a finite probability quantum mechanically there is a finite probability of a particle of being reflected and transmitted. This I have claimed in the first slide, in which I have proved and I have showed you that indeed this is true. And the sum of r and t should be equal to 1. This again comes from the current conservation, that current is conserved. Okay, so here we have seen the case of when the energy of the particle is greater than the potential barrier. Now we will try to see what will happen when the energy of the particle in the step potential is less than the potential barrier. We'll see in the next lecture. Thank you.